Hi, this is Tierney from Monroe Community College, and I'm here with another video. I apologize. My voice may be a little different. I have a cold today, but that's not going to stop me from talking about heat flow and reactions. So we've been talking about heat flow, and as you may recall, heat flow problems are conservation of energy problems, where we have no loss of energy or gain of energy in an overall system. So last time we looked at a metal that we put in water, where the metal was our system and the water was the surroundings. All of the energy that flowed from the metal went to the surroundings, the water, and the amount of energy exchanged was equal but then had opposite signs. So this is a type of problem that is very common, and actually the problems that we look at today are going to be exactly the same, except for now we're going to be incorporating some other Q terms. So each of these Q's I refer to as a Q term. So in this problem we had two Q terms, one for the metal, the system, and one for the water, the surroundings. We're going to be looking at situations where we have reactions today. So let's look at a hypothetical reaction. It's actually very similar to a reaction we're going to be doing in lab class. So we're going to take two solutions. So solution A and solution B, we're adding to our reaction vessel. Yes, our reaction vessel is a coffee cup. We are going to be using the same in lab. And a reaction occurs. Poof! Now this reaction is going to be an exothermic reaction, so it's going to release energy. And when that happens, we need to express that mathematically. And so the reaction itself gets its own Q term in the problem. So I call that Q of reaction Rxn, and this represents the energy that's either absorbed or released during a reaction. So if it's absorbed, then we have an endothermic reaction, and our Q term has a positive value. If it's an exothermic reaction and the energy is released, then we have a negative value for the Q of reaction. So just keep that in mind as we go through here. So there's a couple different ways in the lab that we can measure this Q of reaction. This is called calorimetry, and it's a fancy name, but we're just going to be doing the same types of problems as before, but now they're called calorimetry problems because they involve reactions. So the first type of calorimeter is a bomb calorimeter. It's constant volume, and you have a vessel on the inside where a reaction occurs. Oftentimes this is with a combustion reaction, which is why we have the fire here. So that's happening, and it's surrounded by water. And when we have a combustion reaction, which is exothermic, it heats up the water, and the temperature of the water goes up. We know how much energy it takes to heat up that specific amount of water, so we know how much energy is given off by the reaction. The other type of calorimeter, which we'll be using in class, is the coffee cup calorimeter. It's a lot more simple. It is constant pressure rather than constant volume. So in a bomb calorimeter, the pressure actually builds up, but in this calorimeter, the pressure remains the same. And we simply have an insulated vessel where a reaction, an aqueous reaction, occurs, and we measure the change in temperature as that reaction occurs. If we have an exothermic reaction, we'll see an increase in temperature. If we have an endothermic reaction, you would see a decrease in temperature. So how we go about solving these problems is just like before. It's a conservation of energy problem, which means no energy is gained or lost. So that means we have at least two Q terms, and they're going to be added together to equal 0. So the first thing you need to do is figure out what are those Q terms. Those Q terms come from everything inside and outside of the system that could be gaining or losing heat. All right. So in our coffee cup problem. So if we go back to our coffee cup, notice we have a thermometer. We have the whole coffee cup with the cover itself. That would be referred to as a calorimeter. So that would have a Q term. The solution inside, this would have a Q term, and the stir would have the Q term. So there would be a variety of Q terms in this problem. If there is a reaction occurring, this would also need its own Q term. That would be the Q of reaction, as you may recall. If you have amounts of reactants or products that are given, they do not get their own Q term. They will instead be packaged in the Q of reaction since they're used in the reaction. Finally, we add up all of these Q terms and they equal 0 because the energy coming from one Q term is going to be absorbed by another. So they would be equal and opposite in charge. So the next thing we do is we decide if there's any Q terms that are negligible. So negligible means that it's small enough where it's really not going to affect our calculations. These are going to be any terms that are not directly referenced in our problem, or if they are, it will say that they're negligible. With all of the Q terms that you have left that are not negligible, we are going to be substituting for them. We're either going to be substituting in our MC delta T or our C delta T. Unless you're solving for a Q term and then you're going to leave it in the equation. That would be if you're asked to specifically solve for that Q term. Also, Q of reaction, you never substitute in. So you might want to make a note of that. So you never substitute in for Q of reaction. You will either be given your Q of reaction or will be solving for it. With the other Q terms that you are going to be substituting for, to decide which of these equations you use completely depends on the unit of either your specific heat or your heat capacity. If it has grams in it, you're going to be using MC delta T. If it does not have grams in it, you're going to be using C delta T. Now you're going to substitute in your numerical values and then solve for your missing term. So let's try this out with a problem. We have practice problem 2. When 1.045 grams of calcium oxide is added to just enough water to create 50.0 milliliters of solution at 25.0 degrees Celsius in a calorimeter, the temperature of the water increases. Here's the reaction that occurs. So we have calcium oxide added to water to produce calcium hydroxide, and energy is either absorbed or released. Is the reaction endothermic or exothermic? We're going to base that on the fact that our temperature of our water, it does increase. So that means we have an exothermic reaction. The energy released from the reaction is being used to heat up the water that surrounds it. Now let's get into the numerical part of this problem. Let's calculate the final temperature of the solution knowing that the reaction released 1.7 times 10 to the third joules of heat. Assume the specific heat of the solution is 4.184 joules per gram degree Celsius. The heat capacity of the calorimeter is 17 joules per degree Celsius, and the heat loss to the room is negligible. So what we're going to do is first we're going to identify all of our Q terms. So we have a reaction going on. Whenever you have a reaction going on, write down your Q of reaction. Okay. We're going to add that to our next Q term. Remember that all of our Q terms are going to add up and equal 0. So the next thing we know is that this reaction is occurring in a solution. So the water that's not reacting, that's going to be heated up, and that's what we are taking the temperature of. So we need a Q of solution. You can have that as Q of water if you want to. I really don't care. Either one's fine. We have this happening in a calorimeter. We also see we have a heat capacity of a calorimeter given, so we better have a calorimeter Q term. And we also should always just mention that the heat loss to the room is the Q of the surroundings. So those are all going to add up to 0. Now, it is mentioned that this heat loss to the room is negligible. On a test, you could just totally leave that off. I like to put this in here so that you know that in case we do have a problem where it's not negligible, you've seen it before. So essentially, this is our equation right here. Q of reaction plus Q of solution plus Q of calorimeter equals 0. I'm going to get a fresh new slide. And actually, at the top of the slide, I have summarized everything in the problem. Some students get really intimidated by word problems. This is what I recommend students do if they're very intimidated by problems that have a lot of words and numbers. Just kind of summarize everything for yourself so you can organize it in your mind. So here is everything that's given to us and our equation once again. So once we have our Q terms added up to equal 0, now we're going to try and substitute in. When we substitute in, we are going to be substituting in either MC delta T or C delta T. Let's take this one Q term at a time. So our Q of reaction, as you may recall, you never substitute in for Q of reaction. So we're just going to rewrite that. Our next Q term, Q of solution, now we are going to substitute in. Let's look at the constant value given for our solution. So that is this right here. Notice that we have grams in that constant unit, so we are going to be using MC delta T. So for our solution, we have MC and delta T of the solution. I want you to actually not just put MC delta T, but M of solution, C of solution, delta T of solution, because the mass is unique to the solution. You might have a mass of something else in this equation, and so you want to keep everything straight for yourself. This will definitely come in handy when we do problems in the future and in lab. Our last term, our Q of calorimeter, let's take a look at the constant given for the calorimeter. That's this one right here. Notice there's no grams in the unit, so we're just going to be using C delta T. So that's going to be C of our calorimeter, delta T of our calorimeter equals 0. All right, now our final question asks for T of F. We don't have this in the equation. As we substitute in our numbers, I will be substituting in for both of the delta T's, our final temperature minus our initial temperature. Now, in this case, there was only one initial temperature given, and we're only asked for one final temperature. In all of these problems, we can assume that the final temperature of everything in the system is going to be the same. And since we're only given one initial temperature, that means that our solution and our calorimeter are starting at the same temperature. So actually, our delta T's for the solution and the calorimeter are going to end up being the same. Now you can either solve for delta T now and then substitute in. I'm actually going to be substituting in the TF minus the 25.0 degrees Celsius for the TI right now as I put in my values. So let's put in our numerical values. Our Q of reaction, we are told we release this amount of energy, the 1.7 times 10 to the third joules. That means it's going to be a negative value. That's very important that you keep the signs straight for our Q values. Now we're going to substitute in our solution, knowing that, and since this isn't given for all of these problems, you can assume that all solutions have the same density as water, which is 1 gram per milliliter. So we know that we have 50 milliliters. That's just switch it right over to grams. So 50.0 grams. All right, we can just straight substitute that in. So we're going to substitute in for our values. So we have our 50.0 grams times our 4.184, and we're going to substitute in for delta T. So this is delta T right here, this entire thing. Our final temperature, which we are solving for, minus our initial, which was 25.0 degrees Celsius. Now for our calorimeter, we're going to substitute in our values for that. Again, substituting in for our delta T, TF minus TI. Notice that these two delta T's are equal. That will happen sometimes, but we've seen in the past delta T's can be different. And those are going to all add up to 0. So now what we're going to do is good old FOIL. Do you remember that from algebra? So we are going to multiply our terms. So we're going to multiply this term by this and this, and then our 50 by our 4.184, and then times our TF. And then we're going to subtract from it the 50 times the 4.184 times the 25. So our Q of reaction term stays the same. Our 50 times 4.184, you should get 209. Our grams cancel out, so we just have joules per degree Celsius, and we're multiplying that by our TF term. Now we're going to multiply by the 25 and subtract, and notice that we end up both the grams and the degrees Celsius cancel out, so we just have joules. So we're going to do the same type of FOIL system right here with our calorimeter values. We have our 17 joules per degree Celsius times our TF, and now we're going to multiply the 17 by the 25 and subtract that. So we get 4.3 times 10 to the second. Notice I'm keeping track of significant figures. Notice we have multiplications, additions, and subtractions. That means for each multiplication, you need to keep track of this sig fig right there. So that's why I only have 2 sig figs here. Our 17 only has 2 sig figs. Now, just like in algebra, we're going to collect terms. So everything that's a joule, we're going to add together. Everything that has the TF, we're going to add together. And we end up with this as our problem. So in order to solve for TF, we are going to take, so we put this over on the other side, we add that. So we have our 7.5 times 10 to the third joules. We're going to divide that by our 226 joules per degrees Celsius. Our joules cancel out. Now this is 1 over degrees Celsius, which actually ends up being just degrees Celsius. We're only allowed 2 significant figures, and that should end up to be 33 degrees Celsius. And that is our answer. There is a third part to this practice problem. We are not quite done yet. So based on the information that we have in part B, calculate the energy released in joules per mole of calcium oxide dissolved. Now, we're going to be doing this in lab as well. So we know the energy released was 1.7 times 10 to the third joules. So let's just put that. And we want to know how much energy was released per mole of calcium oxide. And we know that we have, if we go back, 1.045 grams of calcium oxide. So all we're going to do is divide our energy by our moles of calcium oxide. Now, I trust that you can go from grams to moles on your own, right? We're going to use molar mass. Take a moment, pause the video, and do this calculation. Go from grams to moles of calcium oxide right now. Okay, so you should get 0.01863 moles. Okay, notice we're keeping our 4 sig figs. And now we're simply going to divide our 1.7 times 10 to the third joules divided by our 0.01863 moles of calcium oxide. We're going to get units of joules per mole, which is 9.1 times 10 to the fourth joules per mole. Now, because we have an exothermic reaction, these numbers need to be negative. So we're going to end up with a negative number. This is actually a very helpful number. If you have 2 scientists doing this calculation and they use different amounts of calcium oxide. So let's say one scientist used twice as much calcium oxide. Twice as much energy is going to be produced. So this is a way for us to kind of equalize so we can see if the same amount of energy was still released. So this is, as you may recall, an intensive property. And this is a way for us to compare different results. So now let's look at practice problem 3, which is your turn. You're going to treat this very similar to the last problem. Let's take a look at it. In a calorimetry experiment, the temperature of 500 milliliters of water rose from 19.78 degrees Celsius to 23.61 degrees Celsius when 1.0 gram of sodium metal reacted, according to the reaction below. Now, I think your phrasing might be a little bit different. I apologize, I forgot to change that in here. I believe yours says 1.00 grams of sodium was added to enough water to create 500 milliliter solution. That means that we're going to have an ending volume of 500 milliliters, which means it will have a mass of 500 grams. If the calorimeter's heat capacity is 25 joules per degree Celsius and the specific heat of water is 4.184 joules per gram Kelvin, calculate Q of reaction in joules, and I believe that's all I asked for. Ooh, I did not do some editing. I apologize. So just do calculate the Q of reaction. Now we have our reaction here below, and if you're feeling really confident, just stop the video and see how far you can get on this problem. I have a feeling some of you might need a hint to get started. So if you are needing a hint, continue watching. Whichever way you are, we will discuss this problem in class when you get back. So for those of you needing a hint, let's talk about how to get started on this problem. So once again, we need to talk about our Q terms. So we need a Q of reaction because we have a reaction occurring. Now let's talk about what other Q terms we might need. Some students want to include a Q for the sodium metal. That sodium metal is totally reacting, so actually that is going to be included in the Q reaction. So you do not need a Q for your sodium. We do, however, need a Q for the solution that this is taking place in because we are going to be heating up that water. So our Q of our solution is needed. We also need a Q of our calorimeter and the room, the surroundings. Notice that nothing is mentioned about the surroundings, so we can say that that is 0, but we are going to need our calorimeter and our solution because we are given a specific heat and I believe a heat capacity for both of those. Yes. So we are left with a problem very similar to the last one, except for now we are solving for Q of reaction and we're going to be substituting in for Q of solution and Q of calorimeter. I can trust you to do that. There is one thing I want to mention. This unit here is just a little bit different than what we've seen before. So we've seen joules per gram degrees Celsius. These are the same and can be interchanged for each other. 1 Kelvin is the same in energy as 1 degree Celsius. So you can actually just substitute in. You do not need to do any conversions between Kelvin and degrees Celsius. You can actually just cross this out and put degrees Celsius and you're good to go. So give this a try and see what you can calculate for your Q of reaction, and we'll meet up and talk about it in class. So I will see you there.